section 4.3. We're looking at the first application of derivatives, which is to figure out where functions are increasing and decreasing and where their max and mins are. Now, I will say that this particular section has lost some of its awesomeness thanks to the graphing calculator, but still try to do it by hand, because you have to appreciate, really in Cal 2 and Cal 1 also, you have to start to appreciate you're learning what your calculator is, how it's thinking and how it works, and if you were on a desert island, how you would do it. So, and you use those skills. I mean, practicing this is teaching you sort of the thinking behind the computer programming, and that if you want to become a computer programmer, you need to have this type of thinking, because you have to tell, in order for a computer to do what you want, you have to tell it step by step by step in a very specific ways. And that's what's good about doing math, is that it really gets you practicing exactly those types of behaviors. So anyway, so we'll do a little old school math today, section 4.3. So we will define increasing and decreasing functions. And you've probably seen this definition before in college algebra, but we will go ahead and talk about it in here. Let f be a function defined on an interval. I, and let x1 and x2 be any 2 points, on I. Okay, all right, so we have two. We'll first talk about when it's increasing and when it's decreasing. So if f of x1 is less than f of x2 whenever x1 is less than x2, all right, so you're going x1 is to the left of x2, and f of x1 is less than f of x2, what do you think the function is doing? What does that mean graphically? So if this is x1 and this is x2, and f of x1 has to be lower than f of x2.
It's increasing.
Good. So you're here, and then it's got to be doing something. It's got to be increasing over that interval. Okay, so that's what that language means. So we say then f is increasing on the interval I. And then if f of x2 is less than f of x1, whenever, we always like to go from left to right, so I'm going to say whenever x1 is less than x2. It also makes sense. You know what I mean? That just feels better. So now f of x2 is less than f of x1. Well, then that should make sense that then f is decreasing on I. And a function that is always increasing or decreasing on I So if it's always increasing or always decreasing, it's called monotonic. Okay, and that comes up later. That's a good word for later mathematical study, monotonic. We're interested in that. Okay, so the question is, what is the first derivative test for monotonic functions? And this is actually corollary 3 to your best friend in the world, the mean value theorem. And it is that if f prime of x is greater than 0 at each point x contained in AB, then f is increasing on the interval from A to B. Okay? So if you think about what did the mean value theorem tell us? Do you guys remember what the mean value theorem? Recall, the mean value theorem told you that f of B minus f of A over B minus A is equal to f prime of C, right? Somewhere in the interval, you could find a derivative, if it was continuous. You could find the slope of the secant line between the 2 points in the interval, and somewhere there you would have a derivative that would be parallel to it. Okay, and so what this is saying is, well, what if for everywhere on all of AB, your derivative is always positive? Then that would mean your slopes are always positive. And if your slopes are always positive on AB, then the function has to be increasing. That's how you have to kind of convince yourself with that. Okay? All right. Now, if f prime of x is less than 0 at each point, x in AB, then f is decreasing on the interval from A to B. Okay, so this is really, this is some big news, because before you didn't know how to say whether a function was increasing and decreasing other than just looking at it on your graphing calculator. So if you know, say you have an interval from A to B, let's imagine that it's monotonic, so it's always increasing. You know that you can kind of feel like this function, it's either always increasing or always decreasing on this interval. You can kind of feel these slopes to be positive, can't you? So positive slopes means the function is increasing. And negative slopes means the function is decreasing. So you can see how they're negative. Zero slope means that the graph takes a stop, right? It doesn't change. There's not increasing or decreasing. And at the point where it's 0, it's either going to, that's kind of like a boundary point to help us decide from to the left of where it's 0, is it increasing or decreasing? We'll see how to do that in just a second. With what we call the first derivative test for local extrema. Suppose that C is a critical point of a continuous function. Now, what did we learn? That was in 4.1. How do we find a critical point? Okay, so where the derivative equals 0 or is undefined. That makes it a critical point. Suppose that C is a critical point of a continuous function. So in this case, it's only going to be where it equals 0. Well, not necessarily. Function. F, and that F is differentiable at every point in some interval in some interval containing C, except possibly at C itself. then what we have are three little conditions that I kind of run out of room with, and so I'm going to kind of pop them up here. Okay? We have three things that can happen. Let's think about it. All right, we know this is my x. All right, this is, and I'm going to think about f prime. Okay, so this is my critical point. This is my x value, my critical point. Now, if the derivative has negative y values and then positive y values, okay, then that means that the original function f is, on this interval, if it's negative, if it has negative derivative, it's decreasing, right? We just said that. So we know that the function is decreasing and then increasing. And we know that it's at c, it's a critical point. So if it's decreasing and then increasing, what do we have at c? Your choices are min or max.
It's undefined or zero.
Well, doesn't it have to be a min?
Yeah.
Does that make sense? Yeah, we know that the derivative is 0, and in this case it has, or undefined, and it has to be a min because it changes from decreasing to increasing. The derivative changes from negative to positive, which means the original function changes from decreasing to increasing. So if you change from decreasing to increasing, you're going to have a little valley. Okay, so that's a min. So if f prime changes from negative to positive at c, then f has a local min at c. From negative to positive at c, then f has a local min at c. Okay? Now, let me see if I can get some more room in here. Good. Okay. I guess I'll just put them. What happened there? Let me grab this one. Okay, so this is the first concept. So I had to come, ran out of room, so I'm continuing it.
Right
messy?
at 10 o'clock. Oh, yeah, that
Hey.
was class up.
Okay, now the second thing is if we have still a critical point at C, okay, but now our derivative has positive slope, so positive y values, and then negative y values, which means that our original function f is increasing and then decreasing, right? So if we're increasing and then decreasing, what do we have at C? We have a max. All right? So if f prime changes from positive to negative at C, then the original function f has a local max at C. Okay? And then the third thing in the derivative test, and this can happen, is, all right, you still have a critical point, so the derivative is 0 or undefined there, but your derivative has positive values on either side. And if that happens, then the graph is always increasing, right? So f is increasing. So it must mean that it just sort of flattens out there. So it's just flat. Now, it could be that the derivative is always negative, too, throughout, except for the instant where it's 0. And if that happens, then it's just always decreasing and flat. Okay? So if f prime does not change sign, at C, the function has no local extrema there. E. And it either flattens out or flattens or has a vertical tangent. Because vertical tangents can happen when you're always increasing. If you think about it, it's like you just come in and then you just get real vertical. Right there. Do y'all see that? That function's always increasing, but it becomes vertical. So it either gets really flat or it's a vertical tangent. But it doesn't change sign. Okay? All right. So let's look at some examples of how we would work this now. It says, for problems 4 and 5, answer the following questions. What are the critical points of f? On what intervals of f is it f increasing or decreasing? And what points, if any, does f assume a local maximum or minimum value? Okay, so the first thing we're going to have to do is figure out the critical points. So that means that we need the derivative, right? And in this case, we have a well, actually, we're given the derivative. Note, given derivative. And so we want to talk about f if we're given derivative. So to find the critical points, we need to figure out where f prime of x equals 0. So that means where does x minus 1 times e to the negative x equal 0. Now this is already factored, so you just have to set each of your factors equal to 0. So x minus 1 equals 0 or e to the negative x equals 0. Well, this equals 0 when x equals 1, and this is never. You can't do anything. There's no value of x that's going to make that function 0. Okay, and so that answers part A. Those are your critical point, or in this case just one. At x equals 1. Okay, now to figure out where f is increasing or decreasing, we look at the behavior of the derivative to the left and the right of the critical point. So we place the critical point on the number line, and we consider the positive and negativeness of the first derivative. Okay, and so the easiest way to do that is with test values. So we would test a number to the right of 1, like 5, and we would test a number to the left of 1, like 0, and then we could determine whether the function is positive or negative. Yes?
Would you want to pick closer numbers?
It doesn't matter. You can pick any number you want. So the most convenient number is the number that you...
Like later on, maybe this was the max, but then later on...
Well, okay, the question is, even though later on, I'll tell you what, the only place a min or max can occur is where the derivative equals 0. So if I found where it equals 0, there's no later on.
Yeah.
There's no later on.
But if there was no
if there were a later on, like if there were a 5 right here, I would need to pick a number between 1 and 5. Yeah, you split up your x interval and test values within your interval, within your little splits. Okay, so I'm going to test x equals 0, and I plug it into the derivative. So I get f prime of 0 is 0 minus 1 times e to the negative 0, which is just going to be negative 1 times 1, which is negative 1. And all I'm really concerned with is whether it's positive or negative, so it's negative, right? So I know that the derivative is negative for any number to the left of 1. I could pick any number I wanted, and I would get that the derivative is negative, okay? Now, if I pick a value to the right of 1, like x equals 5, or 10,000, or whatever, f prime of 5 is equal to 5 minus 1 times e to the negative 5, and this is just 4 over e to the 5th, which I don't really care what it is. I care that it is positive, right? So I know that it's positive. Okay? Everybody all right? So what does that tell me about the original function? Well, where the derivative is negative, the original function is decreasing. Where the derivative is positive, the original function is increasing. So I can draw a little line here, and I can put it talking about f now. I know that f is decreasing when the derivative is negative, and then increasing here. Okay? And at 1, what do I have? Well, if I decrease and then increase, I must have either a min or a corner. In this case, it's a min because the derivative was equal to 0. If the derivative was undefined there, that would be like a little corner or a cusp. Okay, so this is a min. All right, and so I can say now, to answer the question about f, I can say it's increasing. So f is, or I'll say decreasing from negative infinity to 1, and then increasing from 1 to infinity. So isn't this interesting? I never even looked at the graph. I didn't type it into my calculator at all, and I can already tell you the total behavior of the function, or a lot of the behavior of the function. Now, the truth is, I don't know what the function is. I know what the derivative is. And this isn't an easy one to get back to, the antiderivative. There's no add 1 to the exponent and put it over it for this bad boy.
Wouldn't you know that relatively?
Do you see what I'm saying? Yeah. This is a confusing function. This isn't one that we can just in our heads figure out what the antiderivative is. But I can tell you a lot about the behavior of the original function, which is what happens so much in your physics. Often you can see the rate of change, which is velocity, but you can't describe the original position. But if you know the rate of change, well, then you know a lot about the original function, you know? So it's kind of exciting. All right, part C then. I'm going to get these lines off this paper. It's irritating. Part C says, on what points, if any, does f assume a local max or min? And we already determined, since it changes from decreasing to increasing, we have a local min. So we have a local min at x equals 1. So it's important you understand that we figured out stuff about f from f prime, right? We never knew anything about f. We couldn't type f into our calculator because we don't know what f is. All right. I have it all mine. Okay, here's a bunch of room for this one. All right, this is number 5. We're going to do the same thing. It says, let's look at f of x. Let's find the critical points. That's part A. Critical points are where the derivative equals 0. So f prime of x equals 0. So here, where does x to the negative 1/3 times x plus 2 equal 0?
Negative 2 and 0?
Well, this negative 1/3 is 1 over the cube root of x, which is not actually, that's going to be where it's undefined, right? Yeah, okay, so it's undefined at, so 1 over the cube root of x times x plus 2, it's equal to 0 or undefined is what we're looking for. And so we have x equals negative 2 is a 0, and x equals 0 is where the graph is undefined. So those are both critical numbers. Those are both important numbers, or where the function is undefined. Okay? So B then is we're going to try and figure out where the function is increasing or decreasing. So critical points at negative 2 and 0. So what we do is we put those critical points on the number line in order. So negative 2 to 0, because this is like your x-axis. And you're going to consider the positive and negativeness of f prime so that you can then discuss the increasing or decreasingness of f. And also you'll be able to figure out whether you have mins or maxes. Okay? All right, so we need to pick a number to the left of negative 2 and test it in f prime. So a number to the left of negative 2 would be like negative 3. So f prime of negative 3 is equal to negative 3 to the negative 1/3 times negative 3 plus 2. And you just kind of look at it. You don't have to, I mean, you can calculate if you want, but that's, I guess I will because I'm not sure. The negative 3 plus 2 is negative 1 over the cube root of negative 3, which is negative. And so this is going to be positive. Do y'all agree with that? Okay, so we know that the function, the derivative is positive for any value to the left of negative 2. We just picked 1, and that's all we had to pick. We now know its behavior, all the behavior for the left of negative 2. Now we pick a number between negative 2 and 0, and the easiest one would be 1. And if we do f at 1, that's going to be 1 to the negative 1/3 times 1 plus 2, which is clearly positive, right? So we know it's positive. Sorry, wait.
So 0 would be negative 1.
Yeah, how about we try negative 1, because we want to pick a number between negative 2 and 0. Yeah. Wait a minute, Ms. Brooks. All right, so negative 1. Now, this is negative 1 to the, this is negative 1/3. Okay, so this is 1 over the cube root of negative 1, which is clearly negative, not to me, but to some of the people in the audience. That's clearly negative, and so we have, it's negative here. And now if I do f at 1, it makes more sense to do f at 1 now, because that's a number greater than 0. And so that's going to be 1 to the negative 1/3 times 1 plus 2, which is clearly positive. So what can we say about f? Well, we can say that f is increasing. And then between negative 2 and 0, it's decreasing. And then how about from 0 to infinity? What would y'all say? Increasing. Right? Okay, and then what do we say? If we increase and then we decrease, what do we have? That's a max. And then if we decrease and then we increase, what do we have? A min. But we know that it's actually undefined at 0, so it can't be real smooth like this. It's going to have to be like the little bird, the little corner thing, little cusp thing. Okay? So we would say for this function that it's increasing on the interval from negative infinity to negative 2, union 0 to infinity. Then we would say it's decreasing between negative 2 and 0, and we would say that we have a local max at x equals negative 2 and a local min at x equals 0. Okay? Pretty fun? Hey, Robinson, you guys got to try and pay attention a little bit, or at least fake it, please. It's a little bit distracting. I understand your pain, though, because you're just kind of come in and out, and it's hard to focus. All right, let's try and do problem. Maybe we can do one together. It'll be fun. Y'all want to try one together, Robinson? Do one with me? All right, so you're going to do number 6. Are y'all ready?
Yes, yeah.
Okay, that'll help you stay focused. Okay, so on number 6, we have to find the intervals on which the function is increasing or decreasing, local extrema, and decide whether they're absolute, support your findings with a graphing calculator. You might be like, well, why don't I just do it with a graphing calculator? Well, because I said so. All right, so what's the domain of this function, Robinson? You should always consider the domain first, because, you know, that was one of those weird college algebra concepts you never really liked. But anyway, domain of this function.
All reals?
Yes, negative infinity, positive infinity, because it's just a polynomial. Polynomials are like our favorite functions to play with. Okay. All right, so in order to find the intervals on which the function is increasing or decreasing, I need to find the critical values and then test numbers to the left and the right of the critical values. In order to find the critical values, I need to find where the derivative equals 0. So Robinson, what is the derivative?
0.
No, what's the derivative of this function?
Oh, sorry. Negative 3x squared plus 4x.
Good. Okay, now I want to set that equal to 0, so how should I solve that? Did I hear y'all say something?
Take out an x.
Yeah, let's factor x out, and we'll have negative 3x plus 4 equals 0. Okay, and then what? X equals 0, good, and x equals
And
what,
4/3.
4/3?
No.
Yes? Yes. Okay, so these are our critical points.
Next one, you subtract the 4, and then you divide both by -3.
Are the critical points. I call them CPs. Okay? All right. So then what we do is we draw a number line and we put the critical points in order on the number line. So 0 and 4/3. Okay, and then first we're going to test the numbers to the left, right, and in between 0 and 4/3 into the derivative, not the original function, the derivative, and see whether it's positive or negative, and that'll tell us about the behavior of the original function. Okay, so Robinson, what number do you want to test to the left of 0?
-1.
All right, f prime of -1 will be, or I guess I should be doing h prime, sorry. H prime of -1 is going to be -3 times -1 squared plus 4 times -1. So is this positive or negative?
Negative.
So it's less than 0, so we would say that it's negative. All right, now what's a number between 0 and 4/3?
1.
1. -3 times 1 squared plus 4 times 1, that is,
Positive.
all right, positive. And then a number to the right of 4/3, like, I don't know,
2.
100 or 2. No. All right, and so then -3 times 100 squared plus 4 times 100, you should be able to convince yourself that's negative, right? Okay. Now, Robinson, if you know the derivative is negative, what do you know about the original function's behavior?
It's decreasing.
Is it, if it's negative, it's decreasing?
Yes. If you have negative slopes, you know, as see, kind of imagine if the original function, say this is the original function, if the slopes are all negative, then you can kind of feel it decreasing, right? The slopes of the tangent line. All right, and then between 0 and 4/3, we're going to increase. And then from 4/3 to infinity, we are going to decrease again. Okay, and so this function is decreasing, increasing, and then increasing, decreasing, right? And this, the question was, would we have a corner or a cusp at 0, or is it smooth? And the reason we had a cusp at 0 here was not because it was 0, but because 0 was what made the function undefined. Okay, so if the derivative is undefined, you have a cusp, a corner, or a vertical tangent line. Now, this function is never undefined. It's a pretty parabola. The derivative's a parabola, so it's not going to be. It's going to be nice, smooth. Okay, so we have a local min at 0 and a local max at 4/3. Okay, everybody okay? All right, so part A, to answer this question, is the function is decreasing. Tell me the interval, Robinson.
Okay. Is it the -1?
But it probably
Wait, no,
Go ahead.
would it be negative infinity to 0? Negative infinity to 0?
And, or union,
4/3. 4/3 to negative.
to infinity. Yeah, and it's increasing in between from 0 to 4/3. right? Okay, and then on part B, we have a local min, and we want to figure out what the value is. So of, and you put the 0 into the original function. If you put it into the derivative, it's going to give you 0 because you knew that. That's the critical point. So you put it into the original function, which in this case is, the original function was negative x cubed plus 2x squared. So this will be negative 0 cubed plus 2 times 0 squared, which isn't very exciting. But anyway, it's 0. So we have a local min of 0 at x equals 0. We like to use that language. We say what the y value is. So local min of what the y value is at where the x is. So that's a min, and at the point 0, 0. And then we have, a local max of, it'll be h at 4/3, which will be equal to the opposite of 4/3 cubed plus 2 times 4/3 squared, which if you calculate that, you'll get 32 over 27. So we have a local max of 32 over 27 at x equals 4/3. Okay? And then, I guess that was, is that C? C. We have to decide whether our extreme values are, which, if any, of the extreme values are absolute. Now, these are both local. Can anyone argue why they're local?
Because it goes from negative.
Yeah, your domain is from negative infinity to positive infinity, so you're going to be able to find a more negative x that will be, let's see, we had a min and then a max. So it's going to be a more negative x that'll make it really, really high, and a more positive x that'll make it really, really low. So these are going to just be local. So no absolute extrema because of the domain. If you had a domain that was had endpoints, you could test those endpoints and see whether they were absolute or not. So no absolute extrema because the domain is negative infinity to positive infinity. We don't have any endpoints that we can test on the domain. And then support your findings with a graphing calculator. Okay, so if you type this into your calculator, negative x cubed plus 2x squared and I'll just do a standard window. I can see my min and I can see my max, and I can see it decreasing and then increasing and then decreasing. Does that make sense? All right, I want to show you something really cool. First of all, I'm going to change my window. I'm going to make this like -5 to +5 because that'll just kind of, I'll see it a little bit bigger, kind of zoomed in a little bit. And now, if I were, just for fun, to graph the derivative, -3x squared plus 4x, I can really see, I totally expect the derivative to cross the x-axis at the two places that the original function has critical points. See? Where the derivative is 0, those are my critical points for my original function. See, my derivative crosses at 2, and I had a little max at 2 on the original function. My derivative crosses at 0, and I have a little max, I have a min at 0. Okay? Now here's something else interesting. Just looking at the derivative, do you guys see that the derivative has negative y values? Where the derivative has negative y values, the original function is decreasing. Notice the derivative has negative y values here, and the original function is decreasing. Where the derivative has positive y values, the original function is increasing. Okay? So it's really kind of neat. You can, from the graph, you can sketch the original function. Now, if you don't have like at least a point, you don't know where the original function lives, but you can sort of just sketch the behavior of the original function.
But if you knew the 2 points of the derivative, then you knew where the height was.
Yeah, you have to know something. You can't just have the derivative and really know where it's located. But you can at least know the shape of it. Okay, so that was number 6. Let's try number 7. We have to be careful on number 7. We have to think about the domain. All right, so, and then I'm going to actually move number 8 down to here. So this is number 8, is f of x equals x squared minus 3 over x minus 2. Because I'm going to have to scratch it out because I ran out of room. Okay, so who wants to tell me the domain of this function? Well, you kind of have to think about where this is 0. So 8 minus x squared has to be greater than or equal to 0, right? That's the rule because you can't take a square root of a negative number. So this is negative x squared. It has to be greater or equal to negative 8. So x squared has to be greater or equal to 8, right? So this is kind of like thinking x squared minus 8 has to be positive, right? So what is x squared minus 8? That's a parabola shifted down 8 units. Let's say we're counting by 2s, right? Okay, so it's going to be positive on this side and this side of the interval, right? Is that right? Why is that not what I got last time? Oh, geez. I made a fatal flaw right here. Really, it's better just to not think like that at all. How about we just think at this? Oh, that misworks. I forgot when I divided by that negative, I didn't flip my inequality. Nobody caught it. And that was, let's just think about this, though. This is a parabola flipped and shifted up 8. 1, 2, 3, 4. Let's count by 2s. So it's this, right? And so it is positive between these two critical points, which are plus or minus the square root of 8 or plus or minus 2 on the square root of 2. Okay? So the domain of this function is from negative 2 square roots of 2 to positive 2 square roots of 2. So what's exciting about this function is we'll be able to decide whether the critical numbers are absolute or not. Okay? This is going to be a fun derivative, huh? All right. G prime of x. We have a u and a v, right? And so u is equal to x, so u prime is equal to 1. And v is equal to 8 minus x squared, so v prime is equal, 8 minus x squared to the 1/2 power. V prime is equal to 1/2 8 minus x squared to the negative 1/2 times negative 2x, right? So these cancel. So this v prime is negative x over the square root of 8 minus x squared, right? Okay, so our derivative is u times v prime. So this is going to be x times negative x over the square root of 8 minus x squared plus v, which is the square root of 8 minus x squared times u prime, which is just 1. Okay, so this is a classic problem, so pay attention to the algebra here. Are you okay? Mr. Robinson, you look sad. Are you all right? He threw his hands up in the air. Okay. So this is going to be negative x squared over the square root of 8 minus x squared plus the square root of 8 minus x squared. All right. So you need to get a common denominator. So I'm going to put this over 1. My common denominator is going to be the square root of 8 minus x squared. Y'all with me? And this is one of these classic ones where it happens that you have negative x squared plus, when you do the square root of 8 minus x squared times the square root of 8 minus x squared, you just get 8 minus x squared. Isn't that nice? Over the square root of 8 minus x squared. And so then this is negative 2x squared plus 8 over the square root of 8 minus x squared. And the whole reason you're doing this is you want to figure out where it's equal to 0. And so and also undefined, but it turns out to be undefined at those places where it has trouble in the domain, the plus or minus 2 on the square root of 2. That's going to be where this function is undefined. So you don't have to really think about that. Those are your endpoints. But it's equal to 0 at negative 2x when the numerator equals 0. And so this is going to be x squared is equal, I'm going to move that over and divide by negative 2, so that's going to be 4. So x equals plus or minus 2. Okay? And so these are my critical points. So I will draw a number line. And this one's exciting because it doesn't continue forever and ever. It's negative 2 on the square root of 2, and then negative 2, and then 2, and then 2 on the square root of 2. Okay? And so those are the numbers that you're going to need to test. So what is 2 on the square root of 2? It's like 2.8. So we could test 2.5. Okay? And so, I mean, you know, when you're working these, I don't know. You're supposed to do it. I kind of like do them with my calculator and as a tool to help me because I don't want to be here all day, but you know, you kind of have to just be okay with what you're doing. My derivative was negative 2, make sure you put it in parentheses, negative 2x squared plus 8 divided by the square root of 8 minus x squared. And now if I go to my table and I pick the test values and I look at whether I have positive and negatives in y2, or what I'll do here is I'll take y1 off so it won't even show up in the table. Because I'm only concerned about my test values, the positive and negativeness of my test values in my derivative. So I put my derivative in y2. Now I go to my table. It'll make it easier for me to put numbers in here. Okay, so if I put negative 2.5 in, I get a negative derivative because I put my derivative in y2. So that's negative. If I pick a value between negative 2 and 0, negative 2 and 2 like 0, I get positive. And then let me just go ahead and put the 2.5 in, and then negative. Okay? So I have negative derivative, positive derivative, negative derivative on these places in between my interval. So this is positive, and this is negative. And that's all talking about the derivative, g prime. So what does the fact that the derivative is negative tell you about the original function g? What do we know the original function is doing from negative 2 squared to 2 to negative 2?
Decreasing.
Good. Decreasing. And then between negative 2 and 2, it's increasing. And then from 2 to 2, it's decreasing. Does that make sense? So we are decreasing, increasing, and then increasing, decreasing. So we have a min at negative 2, and we have a max at 2. But we don't know whether they're absolute or local, but we'll be able to determine whether they are if we go ahead and get the y values for the original function at 2 on the square root of 2, negative 2, 2, and then also 2 square roots of 2. And again, I'm going to use my calculator as a tool. Now I'm going to go to my y equals and turn my y1 on. Okay? So now when I go to the table, I can put negative 2 square root of 2 in. And I should get, y2 should say undefined. And y1 will be some value. See, it gives me an error because remember that would have made the denominator 0 of y2. So that's right. The derivative. Negative 2, it should give me 0 for y2, which it does, and then that's the original function value. And then 2 should also give me 0 for y2, which it does. And then 2 square roots of 2. Okay, so,
Put the x values in here because I can't figure out how to do it.
okay. It's probably because your calculator is not set to let you do that. So you need to go to second window, second table setup, and set your independent variable. It needs to be highlighted to ask. See how mine is?
Okay.
And then it should let you. That's a good question. Okay. All right, so we get 0, -4, 4, 0. All right, so this is 0, -4, 4, and 0, right? Okay, so do we have absolute or local? Where are our local extrema? Where are our absolute extrema?
And negative 2.
Right, we have an absolute min, right? And then we have an absolute max. All right, and this is kind of fun because now I have 4 points on my original function. So watch me graph it. I can do, I know -2 on the square root of 2, 0. -2, -4. And I know, I think 0, 0 is on the graph, isn't it? Yeah, if I know that's just something I know. And then also 2, 4. And then this is 0. And so, I mean, it's actually like out there. Okay, and so it looks like this. It's kind of fun. And that's my graph. And it doesn't continue on forever and ever. So let's look at the graphs and see how it looks. And you can kind of see it. Here's the original function, right? And this is the derivative. I don't have enough pixels to show it actually graphing, stopping there at the 2.8 or whatever it was, -2.8. So it looks like it, but it actually does continue to there and there. But notice where this min is where the derivative is crossing the x-axis. And where this max is where the derivative is crossing the x-axis. Notice where the derivative has positive y values, the original function is increasing. Notice where the derivative has negative y values, the original function is decreasing here and then decreasing here where it's negative, where the derivative is negative, right? And this is kind of exciting, and we'll learn about this later, but where the derivative has a max, the original function actually has something called a point of inflection, and it changes concavity. It goes from changing from, like, we call it from holding water to not holding water. But you'll learn about that in another section. But it's kind of, we get to say this again about we get to do the second derivative and talk about the second derivative. Okay. So I think, did we
Miss
answer
Brooks?
all? Yeah?
We're about to have to go, but we had a couple of questions about the test.
Yeah.
Have you been getting our emails? Because you haven't emailed us back.
I got 2 students' emails, and then I don't know, I may have received some more recently.
Okay, and so are you giving partial credit on the test, or?
Yes, but I haven't looked through them yet.
Okay, yeah, we were just making sure you got them. And then the other thing is, are you running the 5K on Saturday?
No.
Why?
Are you?
Yes.
Well, aren't you in cross country?
Yeah, we're taking our team to the 5K.
Oh, you
'cause
are?
we're poor. Yeah.
Oh.
So you should go
tempt
so I
me.
can beat you. What?
Where's the guy?
What did you just say?
That's a challenge, yes.
I know you can beat me, but
So now you have to come. No,
I can't.
no.
I know my coach sort of said no. So.
You're not even on the screen.
All right.
I
Well,
know.
maybe another time.
I know.
Okay. Well, we have to
All right.
go.
Okay. Well,
Okay, thanks.
good luck at the race. I hope you win.
No, probably not. Thanks.
Who else is going to be there?
Probably it's just our team and then a bunch of old people. So. I mean, I'm
That
sure
old,
somebody will
you know,
beat me.
if I tell Paul that you're going to be there, he'll probably go just so he can beat you.
Paul is a beast, though. I know he.
You know that he's an old person and he would beat you. And Pompilio's
Yeah,
probably
but he
gonna
ran.
beat
He
you,
ran
too.
Boston. That's legit. So.
No, he hasn't run Boston.
I thought he ran Boston. Are you
But
sure?
He's so fast. He's way faster than Boston. I've qualified
Faster
for
than
Boston
Boston.
in every race. We're
Yeah.
awesome.
You
How come he gets
are
to be the
okay.
race? All right.
Bye.
See ya. Just because he's faster than me. All right. Here we are, number 8. No, I'm not a beast. All right, f of x equals x squared minus 3 over x minus 2. And we need to find the domain of this function. All right, so can anyone tell me the domain?
Define that. Oh, wait, no, we got it.
Yeah, we have a problem. Houston, we have a problem.
So it's everywhere that's not, it's everywhere that's not undefined, right?
Yes.
Okay, so everywhere that's not 2.
Good. Okay. Everything but 2 would be a good way to say it. So negative infinity to 2 union 2 to infinity. Okay? All right. And yeah, or you can say all real is x not equal to. Okay, let's find our derivative, f prime of x. All right. Well, to do that, we have u over v. And so we need u is x squared minus 3. U prime is 2x. V is x minus 2. V prime is 1. Okay, so we have v times u prime. So 2x times x minus 2 plus u, or minus u times v prime, which is x squared minus 3 times 1, all over v squared, which is x minus 2 quantity squared. Okay, so f prime of x is equal to 2x squared minus 4x minus x squared plus 3 all over this thing. Do y'all agree? Okay, and so this is x squared minus 4x plus 3 over this thing. All right. Now remember, we're trying to find where the derivative is either undefined or equals 0. So we know it's undefined at x equals 2, but that was a domain problem, so that kind of already was aware. Now it equals 0 when f prime of x equals x squared minus 4x plus... careful, Gil. That equals 0 when the numerator equals 0, which is x squared minus 4x plus 3 equals 0. So this is x minus 3 and x minus 1. So at 3 and 1, we have critical points. Also at 2. Okay, and so we will draw a number line, and we will put 1 on it, 2 on it, and 3 on it. Okay, now, if we pick a number to the left of 1, like 0, and we test it in our derivative, let's just see if we can do it in our heads. This will be 3 over a positive number. Do y'all agree? So it will be positive. Now, a number between 1 and 2 is like 1.5, which may be a little trickier for us to do in our heads, so we'll go ahead and steal it with our calculator. So I go ahead and type the original function in because I want to make some statements after this. X squared minus 3. 3 divided by x minus 2. And then my derivative was, what was it? X squared minus 4x. Notice how I put the stuff in parentheses, the numerator and denominator. X squared minus 4x plus 3 divided by x minus 2 squared. What a mess. I'll talk about that in a minute. I'm going to go to the table, and I want to try, what did I try? I tried 0, and I was going to try 1.5, and then I'll try 2.5 and 4. Now, which am I looking at, y1 or y2? Good, because y2 is my derivative. So I got 0.75, which was positive. Then from 1 to 2, I get negative, and then from 2 to 3, I get negative, and then I get positive. Okay, so this is negative, negative, and positive. Okay? All right, now, the function itself is doing what? What is f doing? Well, it's increasing, and then it is decreasing, and then it's still decreasing, and then it's increasing, right? So we increase and then decrease, and then nothing happens. We have actually a vertical asymptote at x equals 2, because that's where the denominator is undefined. And then decreasing, increasing. So we have a max and a min at 1 and at 3. Okay, and so we would say that this function is increasing on the interval from negative infinity to 1, union 3 to infinity, and it is decreasing from 1 to 2, union 2 to 3. We can't say that it's decreasing from 1 to 3 because it's undefined at 2. Okay, now if we wanted to, let's go ahead and figure out what the max and min values are. So if we put 1 into the original function, we'll get negative 3 over negative 2, which is 3/2. So we have a max. Wait, maybe. Okay, if I put 1 in the original function, I have a typo there. I don't get 2, do I? 1, oh, yes, I do. 1 minus, what am I getting? I get 1 minus 3, which is negative 2, over 1 minus 2, which is negative 1, which is 2. So I have a max at the point 1, 2, and then I have a min at, if I put 3 in there, see if I can do this. 3 squared is 9 minus 3 is 6 over, so 3, 1. Sorry, Gail. 3, 6. I have a min, which feels weird, doesn't it? Obviously local. At 3, 6. All right, and then this actually has a slant asymptote if you wanted to graph it. Remember those? Did we do that in here? In the first chapter? Yeah. If you have x squared minus 3, if you do x minus 2 divided by x squared minus 3, you'll get an x there. And that'll be x squared minus 2x. And so then that'll be 2x minus 3, because remember we draw the line and change the sign. And then that'll be plus 2. It'll be 2x minus 4. And so that's going to be, your remainder's 1. But anyway, x plus 2 is your slant asymptote. So if you graph this original function, we have a slant at 2, x plus 2, so and it's up 1 over 1. And we have a vertical asymptote at x equals 2. And we have the max at 1, 2. And then we have at 3, 6, we have a min. Something like this. But anyway, if you look at it, it looks like this. There's your min. And then something like this. Make sense? It shouldn't cross right at 1. It should actually cross it like... It should. I lost a lot there, didn't I? Oh, I can't do that. Yeah, I know. It should cross around like 1.5 or something if you put 0 in. Whatever. That's your graph. Okay? So that's kind of fun, right? I still have another one. Oh, I have 2 more. And it's 10, 12. All right. You're not going to hurt my feelings if you leave. All right, the domain of the natural log, what do we remember? For the natural log function, the domain you have to be greater than 0. So this is from 0 to infinity. You can't take the log of 0 or a negative number. All right, your derivative is, let's not do UV, let's just think about it. The first times the derivative of the second, so x times 1 over x plus the second times the derivative of the first. All right, and so this is 1 plus the ln of x, and we have to set that equal to 0. So this will be fun. Ln x equals negative 1. So this, you have to e it, right? So this is just like a little circle of life. E to the negative 1 equals x. So e to the negative 1 is your critical point. So that's 1 over e. E to the negative 1, you're looking at f prime to help you make some decisions about f. Okay, if you pick a number to the, 0 actually. Okay, if you pick a number to the right of e to the negative 1, like 1,000, and you plug it in here, 1,000 times the ln of 1,000, that's certainly going to be positive. If you pick a number to the left of 1 over e is like 1 e is 2.7, so it's like 1 over 2.7, which is like, if you type in your calculator, it's 0.36, but 1 over 2 is 0.5. So if you pick like 0.1 or something, you'd be all right. And the ln of 0.1, you should know, is negative. So this is going to be negative. But you could use your calculator to help you. Which means that your original function is decreasing and then increasing. So we decrease and then we increase, right? Okay. And so we are decreasing from 0 to e to the negative 1, and then we are increasing from e to the negative 1 to infinity. All right? And so we have a min at x equals e to the negative 1, and the y value is e to the negative 1 ln of e to the negative 1. But you remember the power rule that brings this in front, so that's just going to be a negative 1. Ln of e is 1, so this is just negative e to the negative 1. That's your y value. And so you can graph this. It starts at 0, 0, and then it just has a little min here, and then it goes like that. So this is the point e to the negative 1, comma, negative e to the negative 1, which is like 0.36. Okay. So, and the last problem says, identify the function's local extrema values in the given domain and say where they are assumed. Which of the extreme values, if any, are absolute? So it's just still more of the same. This is an easy one. Okay, we can do this. What's the derivative? 3x squared. What do we do with the derivative? All right, so negative 3x squared equals negative 12. So x squared equals 4, so x equals plus or minus 2. All right, so those are my critical points. My domain is negative infinity, positive infinity. So I look at f prime. If I pick a number between negative 2 and 2, like 0, I plug it in there, I get positives. If I pick a number to the right of 2 and I plug it in there, will I get positives or negatives? And to the left of 2? Careful. Left of negative 2. Left of negative 2. Like negative 4, it's still going to be negative, right? Because you square that. All right. So we are decreasing and then increasing and then decreasing. So decreasing, increasing, increasing, decreasing. So we have a min and a max. And so we can actually figure out, oh, did they give us a restricted domain on this? No. I don't know why I have a restricted domain in my... Oh, I guess originally on the problem I wanted to restrict the domain. Negative 3 is less than or equal to x, which is less than infinity, but I didn't write that. But maybe on that homework there's one where they restrict the domain like that. And if that's the case, then you actually pop this at -3 like that. So you want to test then, you want to find f at -3, f at -2, and f at 2 to decide if you have an absolute or a local min or max. All right, your original function is at 12x minus x cubed. So 12 times -3 minus -3 cubed. If you type that into your calculator, you will get -9. On this one, you will get -16. And on this one, you will also get, or you will get +16. All right, and so you have a absolute, no, this is just going to be, well, let's look at the graph and you'll see. This is, I mean, it looks like you have a min and a max. And it turns out that this is an absolute max if you know that beyond 2, it is always decreasing. And since it stops here, it doesn't go -3. It's not decreasing down anymore, you know. So, or it's, since this -9 was not above the 16, that's how you know that it's, that, so this is the absolute max. And this is a local min at -2. And so if you graph it, let's count by twos. 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. So we have -2, -16, -3, -9, 2, 4, 6, 8. And then +2, +16. So it starts there and goes up like this. And it actually has an x-intercept at 0, 0. So something like that is your graph. Okay, we finished. All right, hope you had fun. And I will see you next time.